Hello and welcome to Support Vector Machines in R. My name is Pete Ferrari and I am with the Simplilearn team, and today we're going to cover Support Vector Machines, SVM, in the R programming language. Support Vector Machine is a binary classifier, a supervised machine learning algorithm, and in this video we will learn what all that means. So what's in it for you? Well, we'll discuss what machine learning is, what classification is, and what is support vector machine. We'll also cover understanding support vector machine, understanding an extension of support vector machine, the SVM kernel, and we'll cover a use case, classifying horses and mules. So what is machine learning? The ability of a computer to learn from data without explicit programming. The machine learns from the existing data and predicts future data. So our data set must contain known outcomes. And it must have sufficient amount of data with those known outcomes so that the machine can learn. Take the data, ingest it, apply the machine learning algorithm. The algorithm learns, creates a model, analyzes the model, and then uses that model to make predictions. Machine learning algorithms come in three major flavors: supervised learning algorithms, unsupervised learning algorithms, and reinforcement learning. And today we'll cover classification under supervised learning. Supervised meaning the data set has known outcomes. If it were unsupervised, it would not have known outcomes, and we wouldn't have the categories or classes necessary for the machine to learn. But under supervised learning, we do have the known outcomes in the data set. And under supervised learning, there are two major types of machine learning algorithms: classification, which we'll cover today, support vector machine, and regression. Classification, you predict categories, and in regression, you generally predict values. So while we look at supervised learning, keep in mind that classification can really be considered multidimensional in the sense that sometimes you only have two classes, yes or no, true or false, and sometimes you have more than two classes. Sometimes you have, say, under risk management or risk modeling, low risk, medium risk, or high risk. And SVM is a binary classifier. It is a classifier used for those true, false, yes, no types of classification problems. And in supervised learning, features are important. If there are a lot of features, SVM may be the better classification algorithm choice as opposed to, say, logistic regression. So with supervised learning, the computer is presented with example inputs and their desired outputs, those known outcomes. And the goal is to learn a general rule that maps inputs to those outputs. For example, bug detection, or customer churn, or stock price prediction. Not the value of the stock price, but whether or not it will rise or fall. And weather prediction, sunny, not sunny, rain, no rain. The classification algorithms generally take past data that we have those known outcomes, train the model, take new data once the model is trained, ingest it into the model, and create predictions. Is it a truck or is it a car? And keep in mind that I said features are important, and the number of features, whether or not those features are applicable to your problem, is a whole different discussion. But in some sense, you know, probably intuitively, that the color of a car really isn't indicative of whether or not it's a car or a truck, but the length of the vehicle, or the number of axles, or the weight, or the amount of seating may be more applicable to the algorithm and to training the model. So what is support vector machine? Support vector machine, or SVM, is a type of classification algorithm which classifies data based on its features. And SVM will classify any new element into one of those two classes. So we'll give it some inputs, the algorithm will segregate and classify the data, and then create the outputs. And next, when we ingest new data, an unknown fruit variable in this example, the algorithm will correctly classify the fruit, apple versus orange. So now let's understand what an SVM is. And if you want to understand support vector machine, you really need a good example. And I know that cricket is a wonderful game. I don't know a lot about it, but I know it's very popular around the world, and we're going to use cricket as an example of SVM. So we'll classify cricket players into batsmen or bowlers using the runs to wicket ratio. So a player with more runs would be considered a batsman, and a player with more wickets would be considered a bowler. And if we could take a data set, say of people, cricket players, with runs and wickets in columns next to their names, we could create a plot, a two-dimensional plot. In this example, clear separation between cricket players considered bowlers and those cricket players considered batsmen. And you don't always have a data set this clean where there is a clear segregation of data, bowlers versus batsmen. But for the sake of understanding SVM, this example does well. So before we do any separation, before we apply any high-level mathematics, let's just take a look at an unknown value, a new data coming into our data set. And that datum, we don't know what class it belongs to. That datum is a bowler or a batsman, we know that much, but we don't know, should we consider that cricket player a batsman or a bowler? And so we want to draw a decision boundary, some type of line separating the two classes, so that we can use that decision boundary to classify the new data point. Of course, we could draw lines. There's a yellow line, a green line, a blue line. There's actually not just 3 lines, but an infinite number of lines that we could draw between those two classes. So which one do we pick? And this is kind of reminiscent of simple linear regression, where we find the line of best fit. We want the line of best separation. We want a line that clearly separates those two groups as much as possible. Once we have the correct line, we would be able to classify the new data point. But in this example, you can see if we pick yellow, the new data point would be a bowler. But if we picked green or blue, the new data point would be a batsman. So we need the one that best separates the data. What line best separates the data? We'll find the best line by computing the maximum margin from equidistant support vectors. Now, support vectors in this context simply means the 2 points, one from each class, that are closest together, but that maximize the distance between them, or the margin. So the word vector here, you may think, well, he really means points, data points. Well, in 2-dimensional space, yes. And maybe even in 3-dimensional space. But once you get into higher dimensional spaces, when you get more and more features in your data set, you have to consider these as vectors. You can no longer really describe them as points, so we call them vectors. And the reason they're support vectors is because the 2 vectors that are closest together, that maximize the distance between the 2 groups, support the algorithm. So that's why we call them support vectors. So if you look at our example, there are a couple of points at the top that are pretty close to one another, and a couple of points at the bottom of that graph that are pretty close to each other. And I'm not really sure, looking at the graph, which 2 are closest, but clearly those points are the ones we need to consider. The rest of the other points are too far away from the rest of the other points. In other words, the bowler points are far to the right and the batsman data points are far to the left. So we'll look at these 4 points to begin with. Mathematically, we would calculate the distance among all of these points, and we would minimize that distance. Once we pick the support vectors, we'll draw a dividing line and then measure the distance from each support vector to the line. The best line will always have the greatest margin or distance between the support vectors. If we consider the yellow line as a decision boundary, the player with the new data point would be considered a bowler. The margins don't appear to be maximum though, so maybe we can come up with a better line. So let's take 2 other support vectors and we'll draw the decision boundary between those, and then we will calculate the margin. And notice now that the unknown data point, the new value, would be considered a batsman. We would continue doing this, and obviously a computer does it much quicker than a human being, over and over and over again until we found the correct decision boundary with the greatest margin. And in this case, if you look at the green decision boundary, the green line appears to have the maximum margin compared to the other 2. And so let's consider this the boundary of greatest margin. And now classify our unknown data value, and now clearly it belongs in the batsman's class. The green line divides the data perfectly because it has the greatest margin, or the maximum margin, between the support vectors. And now we can have confidence in our classification that the new data point is indeed a batsman. Technically, this dividing line is called a hyperplane. And the reason it's called a hyperplane will become a little bit more evident in a few minutes. Generally, in two-dimensional space, we consider those lines. But in three-dimensional space and higher dimensional spaces, they're considered planes or hyperplanes. So we always tend to refer to them as hyperplanes. And the hyperplane that has the maximum distance from the support vectors is the one we want. So, sometimes called the positive hyperplane, d plus is the shortest distance to the closest positive point, and d minus, sometimes called the negative hyperplane, is the shortest distance to the closest negative point. And the sum of d positive and d negative is called the distance margin. So if you calculate those two distances and add them up, that's the distance margin. And we always want to maximize that. If we don't maximize it, we can have a misclassification. And you can see the yellow margin is much smaller than the green margin. So this problem set is two-dimensional because the classification is only between two classes. And so we would call this a linear SVM. Now we're going to take a look at kernel SVM. And if you notice in this picture, this is a great depiction of a plane, not a line. This is three-dimensional space. So that's the plane that separates those two classes. So what if our two-dimensional data looks like this? What if there's no clear linear separation between the two classes? In machine learning parlance, we would say that these are not linearly separable. How could we get support vector machine to work on data that looks like this? Since we can't separate it into two classes using a line, what we're going to do, and clearly there's no line, I mean, convince yourself, there's no line that goes and separates those two classes. So what we would do is we would apply some type of transformation to a higher dimension. We would apply a function called a kernel function to the data set such that the data set would be transformed into a higher dimension, a dimension high enough where we could clearly separate the two groups, the two classes, in this case with a plane, much the same way you saw the picture a few slides ago where the plane was separating the two classes. Here we clearly could draw some planes between the green dots and the red dots. And of course, we could draw an infinite number of planes separating those two classes, but we would draw the one that would maximize the margin. So if we let R be the number of dimensions, then the kernel function would convert a given two-dimensional space to a three-dimensional space. And as I said, once the data is separated in 3 dimensions, we can apply SVM and separate the two groups using a two-dimensional plane. And this is analogous in the higher dimensions. And that last picture on the right-hand side would be some type of depiction of a higher dimension hyperplane. And there are more than one type of kernel function. There's Gaussian RBF kernel, sigmoid kernel, polynomial kernel, depending on the dimension and how you want to transform the data. There are more than one choice for kernel functions. So now let's go through a use case. Let's take a look at horses and mules and see if we can use SVM to classify some new data. So the problem statement is classifying horses and mules, and we're going to use height and weight as the two features. And obviously, horses and mules typically, in general, tend to weigh differently and tend to stand taller. So we'll take a data set, we'll import the data set, we'll make sure we have our libraries. The E1071 library has support vector machine algorithms built in. We'll compute the support vectors using the library. Once the data is used to train the algorithm, we'll plot the hyperplane, get a visual sense of how the data is separated. And if it's two-dimensional or three-dimensional, that's great. Remember, if it's higher dimensional, it's tough to plot those. And then we'll use the new model, the trained model, to classify new values. In general, we would have a training set, a test set, and then ingest the new data. But for our example, we're just going to use the whole data set to train the algorithm and then see how it performs. And once we see how it performs, we'll see, did we get a horse? Did we predict a horse when we had a horse? Did we predict a mule when we had a mule? So here's the R code. Of course, if you want to run this R code, you'll have to install R and then RStudio. Then you'll have to ingest the data, and then you'll have to create an indicator variable to help us with our plots. We'll install our libraries, install the package if you don't already have it installed. I do. And then call the library up into the R session that you're working. We'll create the data frame from the data that was ingested. We will then view the data frame, and of course we have to explore the data frame hoping that we don't have missing values or we don't have outliers. If we do have missing values or outliers, we'll have to either impute those values or delete those values. But in this case, let's hope we don't have any. And now for a quick demo on support vector machines. So we have a working directory where my data is stored, and I'm going to set the working directory to that data source and read the data file into R. And now I'm going to create a vector that really is just an indicator variable. It's the -1s and the 1s that indicate whether it's a mule or a horse. -1 for a mule, +1 for a horse. So I'll create that vector. And SVM, there's a great package, E1071, great library that has the support vector machine functions that we're going to use. And now I'm going to create the data frame. I'm going to take my data and I'm going to add to it the isHorse vector. And now let's just take a peek, and as you can see, there's the height, weight, and whether or not the animal was a mule or a horse. So remember, machine learning, we take a data source with known outcomes, and we apply our algorithm to that data source, in this case a data frame of heights, weights, and the indicator variable. And then we use the machine learning algorithm to learn from that data with those known results. So now let's plot the data, the height versus weight. And as you can see, the horses tend to be a lot taller and weigh a lot more than the mules. So now let's run our algorithm, our SVM model against the data. And the key here is that it's a linear model, and we've run it, and great, now we have a model. Let's look at the summary of the model. And as you can see, there's the formula that it ran and some of the information about the vectors and the classes. And there are two support vectors. So now let's find those two support vectors on our graph. And this might be a little hard to see. The orange outline around this point and this point indicate that those are the two vectors that will support this model, and thus we call them the support vectors. Now let's get the parameters of the hyperplane from the model, and let's plot a line that will be our hyperplane. There's our hyperplane line, and therefore to the left and below are mules, and to the right and above are horses above that line. Let's take a few new observations, and I've encoded these so that it would be illustrative. We'll take these new observations and we'll plot them. And I'm going to generate a new plot, red being the horses, black dots being the mules. I'll create an X and Y axis. I'm going to plot 3 dots, and you can see one of them, the green dot, the first one, kind of falls near the mules. The blue one kind of falls near the horses. And visually, we might conclude, hey, one's a mule, one's a horse. But what about the orange dot? Well, for the orange dot, we really need our hyperplane. We really need something to clearly indicate which side it's on. And of course, by looking at this data visualization, you can tell that the orange dot is probably a mule. And let's verify those results by sticking those observations into our model and predict some outcomes. And down below, you can see that for the 3 data points, 1, 2, and 3, the first one, the green one, was -1. That's a mule. The second one was a +1. That's blue. That's the blue point, which was a horse. And the third one, which we weren't sure about, but clearly the SVM model correctly predicted that that third point would be a -1, would be a mule. And we can visually see that by the hyperplane on the graph. So that's a quick example of SVM. In general, support vector machines are binary classifiers. We don't use them for higher level classification. If you had 3 or more classes, you might want to use something like random forest. What applications? You can use it for face detection, text categorization, image classification, and bioinformatics. Really anywhere that you have the need to classify things into 2 groups. So the key takeaways in this video, we learned about what machine learning is and some of the different types of machine learning algorithms, supervised, unsupervised, and reinforcement learning. And we focused primarily on supervised learning and support vector machines. Understanding support vector machines as a binary classifier and the intuition between the problem and the solution. Take the 2 closest points in the 2 classes that maximize the margin or the distance between them. We looked at what happens if your 2 classes are not linearly separable. and understanding SVM kernel and how you could map a non-linear separable problem to a higher dimension and thereby creating a clear separation. And then we looked at the use case of horses and mules. It's a small data set, but very indicative of how SVM works. And then the applications of support vector machine. And although we only covered 4, face detection, text categorization, image classification, and bioinformatics, there are literally thousands and thousands of applications of SVM. And that's it. If you'd like the code that we use in this example, or you have any questions or concerns, please post them in the comments. We have a great library of these videos up on our YouTube site, and we hope you subscribe to it and watch them all. They're very helpful, especially to beginner data scientists. Thanks again. This is Pete Ferrari, and happy data sciencing.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.